Okay, let me start this lecture by showing you a small video that is part of an experiment that you are going to do later. Okay, so this is known as a combined bending torsion setup, and this is something that you must remember from your ESO 204 course. Now, let me explain the setup. This part is a bar which you can consider to be almost rigid, which is connected, welded basically, to this hollow pipe which has an inner diameter. You can't see that it's hollow, but just believe me that it's hollow. It has an inner diameter of 35 millimeter. So what we are going to do here is we're going to apply some loads on this. We are going to first measure the dimensions and then apply some loads on this so that this hollow beam is going to be under combined bending and torsion. You need to think about this problem. I will give you some pointers, but not everything. You need to think about this problem because this is going to be the subject of our first quiz that is going to be held on September the 7th. So you will see in this video that it's a very uninteresting video, by the way. What you will see in this video is that Anurag ji, our lab in charge, is going to measure the various dimensions. He's going to apply the weights. So you have to think about how the weights are being applied and what the weights are doing to this particular beam. And that is something that I want you to think about. So look at it. Let me play this. As I said, it's a very uninteresting video. Here he's taking the length of the pipe, and it is almost like 75.5 centimeters from the support. Now he's going to measure the bar, the rigid bar. Uh, so it's around 200 millimeters. And now he is with a vernier caliper measuring the outer diameter. So as you can see, the outer diameter is 42 millimeter, and now he's going to hang weights from the point where from the point here from where he measured the dimension. So he is hanging, let me stop it here. Okay, let's play it again. So he measures the length of the pipe, length of the bar, which is like 200, outer diameter 42 millimeters, and now he is going to hang weights from the point from which he measured the length. So the 200 millimeter of this bar that he measured was from this point where he is hanging this thing, and now he is going to put in weights. So you will see that he puts in 3 discs, each of 2 kilos. So a total of 6 kgs is being put in. So this is 6 kgs, 3 weights. And finally, I would like you to look at this top view of the bar. I have put 3 lines. One is along 0 degrees, one is along minus 45, and one is along plus 45 degrees. So these 3 lines I have put right at the top of the circular beam, annular beam. So what I want you to think about is the state of stress at this point O, right at the top of the beam. And then what are the stresses if I take an axis along these two lines? If I take an axis along these 2 lines, what are the states of stress going to be? Okay, Now let me go back to my notes. Let me close this and go back to my notes and try to see how much we can understand about this problem with our basic ESO 204 knowledge. So, okay. So we will not solve this problem, but I will just try to give you some pointers. That point O that I showed is at a distance of W from the wall, let's say, and it's at the top of the circular beam, and this is the rigid bar on which Anuragji was hanging the load. So this L is around 75.5 centimeters, and this is 200 millimeters. So diameter of this bar, this beam, the circular beam is outer diameter is 42, inner diameter is 35. Okay, now if you draw the free body diagram of the beam, so what we are going to look at is at a point at a distance W from the wall, at a point that is located at the top of the circular beam. And this is the cross section along this shaded plane. So this is the cross section. Ri is, as I said, 35 by 2. Ro is 42 by 2. So those are the dimensions of this, and this we can treat as almost rigid. Okay, and the directions, this is our coordinate axis. Z is this way, and X and Y are as shown. Okay, so now um, let us draw the free body diagram of the beam only, the circular beam only. So if you remove the rigid bar, and you had applied, remember, you had applied the load at somewhere here. If you remove the rigid bar now, you will have to replace that with a force, equal and opposite force, and a moment, right? And the moment will be, if this load is P, then the moment will be P times L. So P times D, sorry. So you will have to replace it with a force P as well as a moment P times D. So D here is 200 millimeters as Anuragji measured, and this is now a beam that is subjected to a torque along the x direction equal to PD, and bending load P at the end. Now let us see what happens due to the bending load. We can draw the bending moment diagram. This end is fixed. We can draw the bending moment diagram of this, and then the deflection of the beam due to this load P will be somewhat like this. Okay, and the bending moment diagram would be like this, where the maximum bending moment will occur at the fixed end, and it will be of magnitude PL. I urge you to revise these things, get to remember these things once more, and make sure that you understand that these are the bending moment diagrams that will actually be applicable to this problem. So the bending moment at this end is P times L, and it will be a linear bending moment diagram that goes down to 0 at the right end of the beam. Now this is the effect of this load P. There's also this torque P times D, which is trying to twist the beam. So it's a twisting moment. So so the stress at this point will be sigma xx. That's the only stress due to Euler-Bernoulli bending that we have, and that stress will be given by this formula. That will be given by this formula, where you now have to figure out what this I is, what is the R naught, etc. All these things you will have to figure out. If you plug them in, you will get a value of the stress. You will get a value of the stress. Remember, P is a load due to 6 kilos hung from the end of the rigid bar. L and W are known, R naught is known, I you have to calculate, and that will give you sigma xx, which is a stress acting on the walls of the beam. So this is where you have to find the stresses. That stress is given by this quantity, and the end deflections, if you look at your Euler-Bernoulli beam theory, the end deflections would be PL cubed by 3EI. Okay, now this is all about the bending. As I was saying, that this PD also twists the beam. It also twists the beam. So this is the twisting moment diagram. So if you look at the top view now, so this is the y-axis, this is the x-axis. So we are looking at it from the top. If you look at it from the top, then a straight line going along the x direction due to the twist will become like this. It will twist. It will be fixed at this end because it can't move here. It's a fixed end here, and it will take a shape like this. And then due to this, you will have a twisting moment diagram, which is going to be a constant equal to P times D, which is the twisting moment that you have applied at this end. This has to be balanced by an equal and opposite reaction moment, twisting moment in the other direction. So it has to be constant all over the length of the beam. Okay, so you have now two problems actually which are superposed on each other. So one, you have a bending problem which is kind of solved here, and you have a twisting problem which you have solved here. And I want you to think very carefully about these two problems. I want you to think very carefully about these two problems and make sure that you understand why the bending moment diagrams are like this, twisting moment diagrams are like this, and why this problem is actually a combination of a bending and a twisting problem. If you can get that, then the stresses in the beam due to the twisting moment alone would be tau xy given here. There's another quantity called the polar moment of inertia, which I have denoted as J, and for annular cross section like we have, J is given by this formula. So you would have two stresses. One is a sigma xx, and another one is tau xy. One arising out of the twisting moment, and the other arising out of the bending moment. Again, remember I asked you to concentrate on this point and took a top view of it, and I took two lines which are 45 degrees and minus 45 degree to the x direction, and I sort of urged you to figure out what would be the stress state like along those two directions as well as along the x, y, and z directions that we already have in this figure. Okay, so along the x, y, and z directions, this is the state of stress that you have. Okay, again, I am just telling you this. It is your job. I depend on you to figure out why this is going to be so. So I'm looking at the top view of this point. At this point, right at the top of the beam, this is going to be the state of stress. How much is sigma xx going to be? How much is tau xy going to be is given in the previous slide. Now think about this carefully, and then think about what the stress state is going to be in directions that are at plus 45 degree and minus 45 degree to the x-axis. Apart from that, think of what is the state of strain at this point. What is the state of strain at this point? If the state of stress is this, according to your to whatever you learned in your ESO 204, what is the state of strain at this point in the xy direction as well as in the directions that are at 45 degrees to x and y, 45 degrees and minus 45 degrees to x. Okay, so we will stop here for this lecture, and we'll start with Cartesian tensors in the next lecture.